Hello friends, welcome to today's video lesson on 3-dimensional geometry. The title of today's lesson is Shortest Distance Between Skew Lines. First, let us define what skew lines are. In 3-dimensional space, two straight lines are said to be skew lines if they are non-parallel and non-intersecting. So, first let us define what skew lines are. So, two straight lines in 3-dimensional space are skew lines if they are non-parallel and they are non-intersecting. To give examples of skew lines, let us look at this cuboid. Let us consider a cuboid A, B, C, D, E, F, G, H. In this cuboid, the bottom is A, B, C, D and the top is E, F, G, H. Let us consider two diagonals in this cuboid. Consider the diagonal E, G and the diagonal D, B. These two diagonals are non-intersecting and non-parallel. When we take the diagonals, we mean the lines passing through these two vertices D, B. So, I am considering the line passing through these two vertices, I am calling it the line D, B. Similarly, when we take the diagonal E, G and if we consider the line passing through the vertices E and G, these two lines E, G and D, B are non-parallel and non-intersecting. Let us consider a cuboid A, B, C, D, E, F, G, H. In this cuboid, the bottom is A, B, C, D and the top is E, F, G, H. Let us consider two diagonals in this cuboid. Consider the diagonal E, G and the diagonal D, B. These two diagonals are non-intersecting and non-parallel. When we take the diagonals, we mean the lines passing through these two vertices D, B. So, I am considering the line passing through these two vertices, I am calling it the line D, B. Similarly, when we take the diagonal E, G and if we consider the line passing through the vertices E and G, these two lines E, G and D, B are non-parallel and non-intersecting. Now, the diagonals E, G and D, B are a pair of skew lines. Similarly, if we take the line through the vertices A and C and the line through the vertices H and F, these two also are non-parallel and non-intersecting. Therefore, these two also form a pair of skew lines. Here AC is this diagonal and HF is this diagonal. Again, these are non-parallel and non-intersecting. Therefore, again these two form a pair of skew lines. Now, let us imagine two straight lines passing through these two pens. Those two straight lines are non-parallel and are non-intersecting. Therefore, the lines that pass through these two pens form a pair of skew lines. Now, let us define the concept of shortest distance. Let us take two lines in 3-dimensional space. Say this is line 1, let us call it L equal to 0 and let us take another line L dash equal to 0. Let us say these are skew lines. Say the first line has equation x minus x1 by L1 is equal to y minus y1 by M1 is equal to z minus z1 by N1. Here this is a straight line passing through the point having the coordinates x1, y1, z1. Say this is that point having the coordinates x1, y1, z1, and the direction ratios of this straight line are L1, M1, N1. Let us say the line L dash equal to 0 is of the form x minus x2 by L2 is equal to y minus y2 by M2 is equal to z minus z2 by N2. And here these coordinates x2, y2, z2 are the coordinates of a point through which this line L dash is equal to 0 is passing through. Say this is that point, its coordinates are x2, y2, z2, and L2, M2, N2 are the direction ratios of this line. Now let us define what is meant by shortest distance. Shortest distance of two skew lines is defined to be the length of the line segment which is perpendicular to both these lines, Let us say the line segment AB is perpendicular to both these skew lines. Then the length of this line segment AB is defined to be the shortest distance between these two skew lines. So, the length AB is defined to be the length of the shortest distance between these two skew lines, L equal to 0 and L dash equal to 0. Now, whenever we are given two lines, we can find out the length of this shortest distance. To do this, we may proceed as follows. Any general point on this line 1 can be obtained by taking these fractions equal to small r, and then from here we can calculate the values of the coordinates x, y, z in terms of x1, y1, z1, L1, M1, N1 and r. Then if we take x minus x1 by L1 equal to r, x becomes x1 plus L1 r. Similarly, if we take y minus y1 by M1 is equal to r, we get y is equal to M1 r plus y1. Similarly, when we take this equality, we get z minus z1 is equal to N1 r. So, that gives z is equal to z1 plus N1 r. So, let us take capital A is having these coordinates. Similarly, we can write down the coordinates of capital B in terms of x2, y2, z2 and L2, M2, N2. Let us take all these three fractions are equal to r dash. Then the coordinates of B become x2 plus L2 r dash, y2 plus M2 r dash, and z coordinate is z2 plus N2 r dash. Now, we can find the direction ratios of the line segment AB. The direction ratios of the line segment AB become x2 plus L2 r dash minus x1 plus L1 r, and y2 plus M2 r dash minus y1 minus M1 r, then z2 plus N2 r dash minus z1 minus N1 r. Because we know the coordinates of the points capital A, capital B, we can write down the direction ratios of the line AB or of the line segment AB as the corresponding differences in the coordinates, maintaining order. Now, these direction ratios are obtained in terms of r and r dash. Now, we have defined the shortest distance to be the length of the line segment which is perpendicular to both these lines. So, This line segment AB is perpendicular to both these given lines. Therefore, imposing the condition on the direction ratios of this line L equal to 0 and the direction ratios of the line segment AB, and that these two lines are perpendicular, we can obtain a condition in terms of R and R dash. Similarly, this line segment AB is also perpendicular to the line L dash equal to 0. Therefore, when we impose the condition that these two lines are perpendicular, we get a condition in terms of R and R dash and these direction ratios L2, M2, N2. So, when we apply the condition that this line segment AB is perpendicular to each of these two given lines, we obtain two equations in the unknowns R and R dash. From these two equations in R and R dash, we can solve the values of R and R dash. This is possible because these two lines are skew lines and therefore, they are non-parallel. So, once we obtain the values of small r and small r dash, we can obtain the coordinates of the points capital A and capital B by substituting the values of small r in these coordinates and small r dash in the coordinates of B. Once we know capital A, capital B, we can compute the line segment. We could compute the length of the line segment AB, that is the shortest distance. Here we have to take the modulus value, and we can also write down the equation of the shortest distance, because once we obtain the values of capital A and capital B, we can find the direction ratios of AB, and because we know one of these A and B, we can write down the equation of the line AB. The equation of the line AB is called the equation of the line segment forming the shortest distance, and we may also call it as the equation of the shortest distance line. Well, here we are saying that the line segment AB is forming shortest distance. To clarify this, let us take another line segment between these two lines L equal to 0 and L dash equal to 0. Let us say we have a point G on line L dash equal to 0 and a point H on line L equal to 0, and say this line GH is making an angle theta with the line AB. Then we have AB is equal to cos theta into GH. Cos theta is AB by GH, therefore, AB is equal to GH into cos theta, and here theta is greater than 0, therefore, cos theta will be less than 1. Therefore, we get cos theta into GH is less than GH. I repeat, here theta is a positive acute angle, therefore, cos theta is less than 1, and if we multiply both sides by a positive quantity GH, we have cos theta into GH is less than GH. Therefore, this line segment AB is having the shortest distance, because AB is strictly less than GH, and GH is any other pair of points from these two lines, and AB is the pair of points which form the shortest distance. So, this any other pair, if we call the length of this line segment GH to be a distance between these 2 points, then this distance is strictly greater than this shortest distance. That is how this shortest adjective is meaningful. Well, let us find the equation for the shortest distance line and also the value of the shortest distance between two given skew lines by considering one numerical example. There is another method of calculating the shortest distance. Let us consider again these two lines L equal to 0 and L dash equal to 0. The equation of L equal to 0 is x minus x1 by L1 is equal to y minus y1 by m1 is equal to z minus z1 by n1, and the equation of L dash equal to 0 is x minus x2 by L2 equal to y minus y2 by M2 is equal to z minus z2 by N2. Now, using the direction ratios of these two lines, that is L1 M1 N1 and L2 M2 N2, we can find out the direction ratios of the shortest distance line segment AB. Let us say these are A, B, C. The shortest distance line segment AB is perpendicular to the line L equal to 0. Therefore, we have A into L1 plus B into M1 plus C into N1 is equal to 0. Similarly, the shortest distance line segment AB is perpendicular to the second line L dash equal to 0. Therefore, A into L2 plus B into M2 plus C into N2 is equal to 0. So, between these two equations, we can calculate the ratios of the direction ratios A, B, C. So, here A, B, C are direction ratios. Using these direction ratios of the shortest line segment AB, we can calculate the direction cosines of this line segment AB. That is, we have to divide each of these direction ratios by square root of A square plus B square plus C square. Once we know the direction ratios of the line segment AB, we can write down the length AB in terms of the direction cosines Lmn and these two fixed points x1, y1, z1 through which the first line passes through, and the other point x2, y2, z2 through which the second line passes through. The length AB is given by L into x2 minus x1 plus m into y2 minus y1 plus n into z2 minus z1. Here I am multiplying the direction cosines Lmn or direction cosines of the line segment AB. I am multiplying them by x2 minus x1, y2 minus y1 and z2 minus z1, and I am adding these products, and this is in fact is the projection of the line segment joining these two points x1, y1, z1 with the point x2, y2, z2. So, this numerical expression is in fact is the projection of this line segment joining these two fixed points on this shortest line segment, and when we take the modulus value of this expression, it gives us the length of the shortest distance. Now, let us consider a numerical example. Consider two straight lines x minus 3 by minus 1 is equal to y minus 4 by 2 is equal to z plus 2 by 1, and x minus 1 by 1 is equal to y minus 7 by 3 is equal to z plus 2 by 2. For these two straight lines, let us find the shortest distance and also its equation. Let us say the shortest distance line segment AB, the shortest distance line segment AB is having the direction ratios as small a, small b, small c. Now, the shortest distance line segment is perpendicular to each of these two given lines. Therefore, here for the first line the direction ratios are -1, 2, 1, and the direction ratios of the shortest distance line segment is AB and its direction ratios are A, B, C. Now, this first line is perpendicular to the shortest distance line segment. Therefore, we have A into -1 plus B into 2 plus C into 1 is equal to 0. Similarly, the shortest distance line segment is also perpendicular to the second line. The second line is having the direction ratios 1, 3 and 2, and for the shortest distance line segment AB, the direction ratios are A, B, C. These two lines being perpendicular, we have A into 1 plus B into 3 plus C into 2 is equal to 0. Now, from these two equations, we can obtain the proportion of the DRs A, B, C. Let us obtain the values of A, B, C's by the cross multiplication method. Let us look at the coefficients. These are -1, 2, 1, and these are the coefficients of A, B, C. We have to maintain the same order in the second equation also, and here the corresponding coefficients are 1, 3 and 2. and take this first column again as the fourth column, and take A between these second and third columns, and B between third and fourth columns, and C between first and second columns. Now, multiply these two first and then multiply these two and subtract the second product from the first one. We have A by 2 into 2 is 4 minus 3 into 1 is 3 is equal to B by multiply 1 by 1 is 1, then multiply 2 by minus 1 is minus 2 and subtract the latter one, that is 1 into 1 is 1 minus 2 into minus 1 is minus 2. Similarly, do it for C. So, it is C by minus 1 into 3 is minus 3 minus multiply 1 by 2 is 2, subtract that. So, it is C by minus 1 into 3 is minus 3 minus 1 into 2 is 2, and 4 minus 3 is 1, 1 minus of minus 2 is 3, this is minus 5, and therefore, the direction ratios of the shortest distance line segment are A, B, C, they are 1, 3 and minus 5, and the corresponding direction cosines are found as follows. Now, this is equal to 1 by square root of A square plus B square plus C square, that is 1 square plus 3 square plus minus 5 whole square, and this is equal to 1 by 1 plus 9 is 10 plus 25 is 35. So, this is root 35, and therefore, the direction cosines of the shortest distance line segment are L equal to A by square root of sigma A square. So, it is 1 by root 35, and M is B by this one, that is sigma A square under root, that is 3 by root 35, and C is the direction cosine N is equal to C, that is minus 5 by root 35. Right? If A, B, C are direction ratios, the corresponding direction cosines are A by root sigma A square, B by root sigma B square, C by root sigma C square. Here I have computed 1 by root sigma A square. So, it is A into this quantity will be giving us the direction cosine. So, the direction cosines of the shortest distance line segment are 1 by root 35, 3 by root 35 and minus 5 by root 35, and therefore, the length of the shortest distance is modulus of L into x2 minus x1 plus m into y2 minus y1 plus n into z2 minus z1. Here x1, y1, z1 may be taken to be 3, 4 and minus 2. The first line is passing through the point 3, 4, minus 2. So, this may be taken as x1, y1 and z1. The first line is passing through x minus x1, y minus, right. This should be taken as x minus x1, therefore, x1 is 3. Similarly, if this is taken as y minus y1, y1 is 4 and this is taken as z minus z1, z1 is minus 2. Therefore, the first line is passing through the point 3, 4, minus 2. Similarly, the second line is passing through the point 1, 7, minus 2, and this order triple 1, 7, minus 2 is taken as x2, y2, z2. So, x1, y1, z1 are the coordinates of a point through which the first line passes through, and x2, y2, z2 are the coordinates of a point through which the second line passes through. And taking those 6 coordinates here, we know the values of x2 minus x1, y2 minus y1 and z2 minus z1. We have to substitute those coordinates here. We also know the values of L, M, N. L is 1 by root 35, M is 3 by root 35, N is minus 5 by root 35. So, all the values of this all the variables in this expression are known. Substitute them and compute this modulus value, that gives us the length of the shortest distance. We can also find the equation for the shortest distance line, right. The equation is given as follows. The equation for the shortest distance line segment AB line segment is given by modulus of x minus x1, y minus y1, z minus z1 L1 M1 N1, L1 M1 N1 and L M N equal to 0 and determinant x minus x2, y minus y2, z minus z2, L2 M2 N2, L M N is equal to 0. These two equations together form the equation for the shortest distance line segment. Here x1 y1 z1 is a fixed point through which the first line passes through. We may take it as 3 4 minus 2 and L1 M1 N1 are the direction ratios of the first line, those are minus 1 2 1 and L M N may be taken to be the direction ratios of the shortest distance line segment, those may be taken to be 1 3 minus 5. Now therefore, this equation is equation this of a plane. Similarly, the second equation is also an equation of a plane. Here x2 y2 z2 is a fixed point through which the second line passes through. We can take x2 y2 z2 to be the order triple 1 7 2 and L2 M2 N2 are the direction ratios of the second line. They are 1 3 2 respectively. Here L M N may be taken to be the direction ratios of the shortest distance line segment. Therefore, those may be taken to be 1 3 minus 5. Now, once we substitute these values, again this also represents a plane and the intersection of these two planes give us the equation for the shortest distance line segment. In fact, here this first equation is the equation of the plane which passes through the first line and also contains the shortest distance line segment. Similarly, the second equation is the equation determined by the second given straight line and passes through the shortest distance line segment, and therefore, the intersection of these two gives us the equation for the shortest distance line segment. In this lesson, we discussed two concepts called skew lines and the shortest distance between them. We discussed two methods to find out the length of the shortest distance between two skew lines and to find out the equation of the line segment forming the shortest distance.